Today I'll be covering the topic of isomers. There are lots of different isomers and I'm going to cover each of them. So what are isomers? Isomers have the same molecular formula. And so isomers can be classified as constitutional isomers or structural isomers, and they differ in the way the atoms are connected to each other. And so constitutional isomers are different compounds. Let's look at an example. So C4H8, let's consider this. So you have 1, 2, 3, 4 carbon atoms, and you have 8 hydrogens, 3, 4, 5, 6, 7, 8 hydrogens. So this green is a double bond. Okay, now let's look at another model right here. It has 4 carbon atoms, 1, 2, 3, 4 carbon atoms, and it has also 8 hydrogens, 1, 2, 3, 4, 5, 6, 7, 8. So these two molecules have the same molecular formula, but they differ in the way the bonds are connected, and hence they are called structural isomers or constitutional isomers. Let's look at another example. In this case, the molecular formula is C6H10O, and this molecule right here, an alcohol, has the same molecular formula as the epoxide right here. So these two are considered to be constitutional isomers or structural isomers. They'll have different physical and chemical properties. So let's now consider conformational isomers. So conformational isomers are the same compounds, but they differ in rotation only about a sigma-sigma bonds, and so they rapidly interconvert at room temperature. They cannot be isolated. So let's look at an example. So in this case, the bond, carbon-carbon bond, is being rotated by 120 degrees. And so all the substituents attached to this particular carbon atom is going to move by 120 degrees. So currently the bond angle between the ethoxy group and the methyl group is 120 degrees. So when you rotate it, ethoxy group will move here, and so you have the new conformer. You have the new conformer where the ethoxy group is right here on the top. The methyl group is down. So these two are called conformational isomers. And if you recall, I have a video on conformers. This particular isomer is called the anti because the two methyl groups are opposite each other. And this conformer is called Gaussian because the angle between the two methyl groups is about 60 degrees. So watch my video on conformers to learn more about them. So this is another example. This is an example of methyl cyclohexene, and you can have it in a chair conformer or a boat conformer. So this is a model right here. This is the chair. If you can see, this is the chair conformer, and this is the methyl group right here, and this is the hydrogen attached to the carbon atom. Okay, so this can form. This is the boat conformation. This is the boat conformation. Okay, and in this particular case, then it can flip to give you another chair form. It can give you, so you started with this where the methyl group is axial, and you can flip it around and you can have the methyl group in equatorial position. Okay, so all these are conformations because they readily interconvert at room temperature by just rotation about a sigma-sigma bond. We'll not talk about stereoisomers. So stereoisomers are also isomers, but the only thing they differ is in the arrangement of the atoms spatially in 3D form. So let's look at some examples. So stereoisomers are further subclassified into enantiomers. So what are enantiomers? Enantiomers are molecules that cannot be superimposed. So let's look at an example. Consider the chiral carbon right here in the center. It is chiral because it is attached to 4 different substituents. So this is the methyl substituent. This is the hydroxy group. You have a hydrogen right here, and you have a deuterium right here. So it's attached to 4 different substituents, and hence this atom, carbon atom, is chiral. It's called the asymmetric carbon. And I have the same exact molecule right here. Okay, and you can see that these two molecules are mirror images of each other, just like a left hand and a right hand. And so these are called enantiomers. They cannot be superimposed. So they are considered to be object and a mirror image. If you have not learned about R and S notations on how to find the absolute configuration about the chiral center, please refer to my video on R and S as well as D and L notations that I used to assign configurations about chiral center. So stereoisomers that are not enantiomers are called diastereomers. And diastereomers have 2 or more chiral centers. So this is an example of a diastereomer. It has 2 chiral center, one right here, and this one is the second one. And you can see the absolute configuration at this chiral center is S. The absolute configuration at this chiral center is R. These 2 molecules are diastereomers because they are not enantiomers. You can see the only difference between these 2 molecules is the absolute configuration about this chiral center right here. So the absolute configuration around this chiral center is R, and for this carbon it is S. So these 2 molecules are diastereomers. So you can see that bromine and methyl group are switching places in this 2. Hydrogen is at the same location. So let's see what mesodiastereomers are. So stereoisomer with 2 or more chiral centers, but which has an internal plane of mirror due to identical substituents at each chiral center, is considered to be a mesodiastereomer. A mesodiastereomer will not rotate a plane of plane polarized light. So it is achiral. So let's look at this example right here. So look at the carbon atom. This carbon atom has S configuration. Look at the three substituents: hydrogen, ethoxy group, and methyl. The substituents on this carbon atom is identical: hydrogen, ethoxy group, and methyl. So the substituents on the two chiral carbon atoms are identical. And because they are identical, there is an internal plane of mirror. And so these two are considered to be mesodiastereomers. It's essentially one and the same molecule. The object and the mirror images are superimposable. Let's consider another example of cyclohexane 1,2-diol. So let me make this molecule quickly. It's cis. So okay, so you can see this is cyclohexane 1,2-diol. These are the two. This is one OH group, this is another. So we have two OH groups, and they are on carbon atom 1 and 2. They are on the same side of the plane of the ring, and they are on the top face. So they are cis. And this is the chair conformation for this molecule. In the chair conformation, you can see one of the OH group, this OH group, is in axial position, whereas this OH group is in equatorial position. And if you flip the ring, then you'll see that the OH group that was in the axial position is now in the equatorial position, whereas the other one has now moved from equatorial to the axial position. So other thing to look at it is look at the molecule this way, and there can be a plane of mirror right through this bond, carbon-carbon bond, okay? And it will be the left half of the molecule will be the mirror image of the other half. So remember that a mesodiastereomer will have an internal plane of mirror. If you can find an internal plane of mirror for a molecule that has two or more chiral centers, then that molecule is called a mesodiastereomer. So I have a few more examples for you which have internal plane of mirror. This is 1,2-dimethyl cyclohexane. You can draw internal plane of mirror right here. This is tartaric acid. It also has an internal plane of mirror. And this is another molecule which has an internal plane of mirror. So let's talk about geometric isomers. So what are geometric isomers? So geometric isomers are diastereomers that differ in orientation of substituents on a carbon-carbon double bond or on a ring. So there are two types of geometric isomers. They are cis and trans. So let's let's try to make some models and help better understand what a cis and trans isomer is. So let's look at this particular example. This is the double bond right here, and you have one ethyl group, CH2 and CH3. So this is the ethyl group attached to the one of the carbon double bonds, and this is a methyl group attached to one of the carbon double bonds. So in this case, as you can see, the two hydrogen atoms are on the same side of the double bond, and so this isomer is called the cis isomer. And this is an example of a cis isomer. You can see this is the methyl group and this is the ethyl group, and the two hydrogens are on the same side. So in case of trans isomer, you have the two hydrogens on opposite side, and so this nomenclature is used for di-substituted alkenes which bear hydrogen atoms on each of the carbon atoms carrying the double bond. So this is the example of a trans isomer. So this is carbon-carbon double bond, this green one, and then you have a hydrogen on one side and the other hydrogen is on other side. So they are on the opposite sides of the double bond, and so this is called the trans. This is called the trans isomer. So let's look at geometric isomers and trans isomers for a ring. So in case of a ring, this is a cyclohexane ring, and you have two OH groups on the cyclohexane ring. The two OH groups are on opposite sides of the ring, and so it's called the trans isomer. This can also be written as like this, where you have the wedge which points towards you, and this is the hash which points away from you or below the plane of the ring. So I have a model right here, and this model is for this is a cyclohexane ring. So let's count the atoms: 1, 2, 3, 4, 5, 6. So there's 6 atoms, and this is cyclohexane, and this is a oxygen atom with hydrogen. So this is the OH group, and then we have another OH group. So they are on adjacent carbons, and if you look at the cyclohexane ring like this. This is both the OH groups are on the same side of the ring. They're on the same side of the ring, and so this is a cis isomer. And if they are on opposite sides of the ring, then it's considered to be a trans isomer. So let's make a model of that so that you can see. So this is the example of trans isomer. So you see this is the ring. This is the plane of the ring right here, and then you have OH group on one side of the ring and the other OH group is on the other side of the ring, and so they are on opposite sides, and so it's called a trans isomer. So right here, so this is the plane of the ring. Okay, you have OH groups on opposite sides, so this is the trans isomer. It's always good to make models to better understand the stereochemistry. I have made this model using the organic chemistry basic set sold by Maruzen. You can buy any other set, but I think making the models is very useful to better help you understand. So let's look at tri and tetra substituted alkenes. So you'll always come across tri and tetra substituted alkenes in organic chemistry. The nomenclature is a little bit different. You use the E and the Z. E means that the high priority groups attached to the double bonded carbon atoms are on opposite side, and then it's called E, but if they are on the same side, it's called Z. So in order to, so the way, let's look at an example to learn how to find the higher priority group. So we have to look at each of the carbon atoms. So in this case, carbon atom 1 has a substituent hydrogen and a chlorine. So between hydrogen and chlorine, the atomic number of chlorine is higher, and therefore chlorine is considered to be a higher priority group as compared to hydrogen. Then we have to look at carbon atom 2 and consider the two groups attached to carbon atom 2. So you have the methyl group that's attached and an ethyl group that's attached. So in order to find out which group has a higher priority, we follow the R and S rule to determine the priority. Please refer to my video on R and S rules to better understand it. So let's look at let's look at the example of how to assign the ENZ stereochemistry to tri-substituted and tetra-substituted alkenes. So let's start with the simple same example. So you have the carbon-carbon, this is the carbon-carbon, this is the carbon-carbon double bond, you have the carbon, this is the bromine atom, this is the hydrogen atom right here, and you have the ethyl group CH2 and CH3. So this is the ethyl group, and here this one is the methyl group. Okay, 1, 2, 3 hydrogens, and this is the carbon. So this is the methyl group. So so in order to find out which whether ethyl and or the methyl group, which one has a higher priority, you look at the atom that is attached to the double bond. So in this particular case, you have a carbon atom attached and a carbon atom attached to the double bond. So you cannot find out which of the substituent has high priority. So then you look at the atoms attached to each of this carbon. So to this particular carbon atom, you have a hydrogen, and a carbon attached. Whereas for this particular carbon, you have only 3 hydrogens attached. And because the carbon atom has atomic number of 6, hydrogen is atomic number 1, and therefore this particular ethyl group or ethyl substituent has a higher priority over the methyl substituent. So we just follow the RNS priority rules. So let's look at the Z isomer and how to name it. So this is the example. Again, you have the chlorine atom right here, you have hydrogen, you have the ethyl group, and this is the carboxyl group. You have this is the oxygen atom, carbon, this is the double bond, carbon oxygen double bond, and you have the oxygen and hydrogen here. So this is the OH group right here. So this whole group is the carboxyl group, and this is the ethyl group. So in order to find the priority between these two groups, you first look at the atoms attached directly to the carbon atom bearing the double bond. So this is the carbon atom bearing the double bond. To this particular atom, you have a carbon atom attached and a carbon atom attached. So just looking at the carbon, you cannot figure out the priority. So you look at the substituents attached to each of these carbon atoms. So for this carbon atom, you have a hydrogen, and a carbon. Whereas for this carbon, you have an oxygen and oxygen. So oxygen atomic number is higher than that of carbon. And so this carboxyl group has a higher priority over the ethyl group. And now, since the higher priority groups are on the same side, so this is higher priority group and this is higher priority group. Since the two higher priority groups are on the same side, and therefore this is considered to be the Z isomer. Isomers. Let's move on to another type of isomer called epimers. So epimers are typically only seen for simple sugars like glucose, fructose, and so on and so forth. In epimers are diastereomers, but they differ in the absolute configuration at only one chiral center, and that chiral center should be the same numbered chiral center. Let's look at an example. So this is an example of D-glucose and D-mannose. You can see this is the Fisher projection structure. If you don't know how to write the Fisher projection structure, please refer to my video on Fisher projections. You'll learn how to convert a 3D structure into a Fisher projection. So in this case, the carbon atom 2, which is chiral, has the OH group on the right for glucose. In case of mannose, the OH group at carbon atom 2 is on the left, and hence these two compounds are called C2 epimers. Let's look at another example. So in this particular case, the carbon atom 3, which is chiral. The OH group is on the right for ribose and is on the left for xylose, and hence they are called C3 epimers. That's carbon atom 3 epimers. So let's move on to last type of isomers called anomers. So anomers are diastereomers, and they are also observed only in sugars, monosaccharides like glucose and fructose, and they are formed because these molecules prefer to form a 5-membered or a 6-membered ring. So let's consider D-glucose. So in D-glucose, the OH group at carbon atom 4 can attack the carbonyl aldehyde right here, and it can form a 5-membered ring. The OH group on carbon atom 5 can also attack the carbonyl group to form a 6-membered ring. The 6-membered ring is typically favored over 5-membered ring, just because the chair conformation of a 6-membered ring is strain free. It has less bond angle, it has no bond angle strain and less steric strain. So D-glucose exists as D-glucopyranose in 99.6%, and the other 0.4% is in the form of a 5-membered ring, which takes the shape of an envelope. I have explained the structures of cyclohexane and cyclopentane in another video called Conformations. Please refer to that video for additional information. So this is D-glucofuranose, and it is just 0.4%, and it has an envelope shaped conformer. So D-glucose in the straight in a Fischer projection or straight or open chain is about 0.03%, so very small amounts, and it equilibrates rapidly between the D-glucopyranose and D-glucofuranose structure. Thanks for watching. Like and subscribe.